What's up, algebra amigos and amigas? I'm Luke Forsberg, and I'm here to teach you about the history of algebra, and I most definitely did not do this the day before it's due. Alright, so let's start into 4th century BC, where Euclid was able to come up with the idea that AB squared equals A squared plus B squared plus 2AB, which it looks a lot simpler when you draw it out like this. And also, it's not that hard to think about. I mean, if you just multiply these two together, then you would get that. So, that's the beginning of this. Fast forward a few centuries later, and you get a guy by the name of Al-Karaji who was able to solve the binomial theorem all the way up until the nth term. And so, for a little timeline, here we have, just to help you understand a little more, we have the dinosaurs, and then we have the pyramids, and then we have the Stonehenge, and we're here. So, yeah, you're welcome. Okay, fast forward 1 century later, and you get a guy by the name of Omar Khayyam, who was able to prove it all the way up until the nth term. He was able to do what Al was not able to do. And then, fast forward 2 more centuries, and you get a man by the name of I practice, I promise. Zhu Shij, who was able to actually make come up with this idea of a binomial / Pascal, which it started as a binomial, but it later became called the Pascal triangle. And it's pretty much the binomial theorem, but put into like this shape. So you start with 1, and then all the corners, the sides are going to be 1. And then to bring it down, you add the 2 numbers above it together. And it slowly forms a bigger and bigger triangle. Alright, and then last we have Sir Isaac Newton. And he was able to expand this whole theorem using calculus. So then that you could plug in fraction terms, negative terms, and everything in between pretty much to make it so you could do more things for n. And that is the history of the binomial theorem.
Thank you, Luke.
You're welcome.
So today I'm going to be talking about how the binomial theorem actually works. So this is the equation that is commonly written as, and you can probably understand most of it because you know these sum symbols and how to distribute with these types of equations, but it's really too complicated for what the binomial theorem actually is. So what's probably easiest is to work with its quotient. So this is the quotient of the equation, and you probably recognize it because we worked with it last chapter. And so you just take your n and k and you plug and chug, basically. And so now I'm going to show you another way that is also really easy to work with the binomial equation using Pascal's triangle. So to find the answer much easier using Pascal's triangle, say we want to find n and k of 5 and 4. You're going to want to drop down the triangle to where you find your first 5 directly after a 1. So that would be this 5. And then you're going to count 5 over, because you always count 1 more than this second number, the k. You count 1 more over. So the answer to n and k 5, 4 would be 5. So Pascal's triangle is another easy way to find out solutions to the binomial theorem. So probably the easiest way of all is to use your calculator. So come here. So you're going to want to input, you're going to want to click math, and then you're going to get prob, and you're going to click 3 once you're there. And so once you're here, say we have n and k 7 and 4. You're going to input 7 to the first slot before the C, and then you're going to input 4 in the second slot after the C. And so once you hit enter, you get 35 right there. And so that's a really quick way using your calculator to find solutions to the binomial theorem. So, some real-world applications for the binomial theorem are things like economics. They use it a lot in the U.S. economy to calculate risk and profit in different like deals and things like that. And they also use it in architecture to find how much the cost will be for projects. And they use it a lot just in probability in general. Again, bringing it back to the U.S. economy. And so, yeah.